Welcome back to dsgn380, the shaft videos. There's at least two. Last video we finished up with this positioned and shaped shaft under these positioning components with a shaped shaft. Everyone's looking okay. We're not detailed yet, so we're getting there. This is a good time to save, I would say. So, save. For me is Command save or Control save. I'm going to say shaft shaped so we can see this later if I screw up this video, essentially. If we go out and have a look at our part, we're in the components folder here, go up one level. And we can see here we're at V2. I'm using this. And it uploads a little bit. You can see we created it earlier with some bad videos. And now we've got shaft shaped. If we want to go back to this, we can. It's good enough for us right now. Okay, let's start with the ring grooves and the rings. Again, the whole point of this video is to use the components themselves to shape the shaft correctly. There's a lot of advantages to this. One of the disadvantages, unfortunately, is that if we change the components, we have to change the shaft. Well, not too bad, like we can survive. Let's try using just ring grooves for everything with rings. Depending on your industry, you might not be expected to put a ring in front of a bearing. I believe that it's not a bad thing. Can be designed for. Usually the advantage of rings are they're outboard of, for example, out here, they're completely outboard of any torque that's running through the two gears, which is only being carried by this heavier middle part anyway. So this is probably safe-ish, and it might increase the diameter slightly, but these diameters are usually the strength of the gear and the load they're expected to take usually takes into account that there's a ring on the outside. Out here, there's no torque nor really any moment, so ring grooves outboard of bearings at the ends of shafts usually don't have much effect on the diameter and the calculation times. So given that caveat, we're going to go ahead here and put some ring grooves in. After that, the plan is to do fillets. So we'll do a fillet for this stuff, make sure it all works out correctly. We'll check the bearing designation or technical data for that, get the right fillet. And then we'll put in our keys and then we'll be done. Moving along. So let's start with placing keys, surprisingly. The same sort of approach as we did before. We've got a whole bunch of work done down here. And you can see we've got joints galore. I'm just going to keep going with placing and jointing. So it's tempting to put them further back, but to keep the flow smooth between videos, I'll just continue on from where we are. So, McMaster-Carr. But before we go, what's the size of that? 25 in diameter. So remember that. 25. We need a ring. Retaining ring, or whatever you want to call it. External, because we're on the outside. And let's make this a little bigger so we can see what's going on. We're in metric shaft, and our size was 25. It's controlled by the OD. Click that to select it. It'll give you only what they have. So we filter down, and black phosphate is fine, right? We don't know exactly what's going on with the rest of the shaft. We haven't been told. So let's just go with standard spring steel phosphate coated, parkerized usually. It's got a standard, perfect. And let's have a look at that. Don't want a PDF. How about a step? Let's have a look. There it is. Some sizes. And it actually has groove widths and all that stuff in here. There they are. So this will not only tell us with a finger, this will not only tell us what we're doing with the ring itself, but also the groove that it is expecting to see. This is good. I'm going to go ahead here and take a screenshot of this. Used this before, obviously. The thing is with these, there's my screenshot. Just making sure I can still see it. There we go. So the problem with these is that they're not the problem. They're modeled as shipped, so they'll actually be smaller than what we're going to be seeing it in place. It's okay. We'll just have them overlapped. You'll see what I'm talking about in a second. These are quite inexpensive, so that's good. And everything looks right. So this is for a 25 millimeter. That's what we've got. After all that, download. There it is. I'm going to leave it as is right now, or we could rotate it. Doesn't really matter. Make it a little easier. Say okay. Not grounded. No. And I'm going to immediately joint this. Joint. Now, the assumption is it's going to be pushed up against the gear. Sorry, bearing. So same approach as before. The inside edge of the ring and the inside just above the fillet for the bearing. Because it's got a gap here. There it is. That's the overlap. Leave it at 0. You can see it on the bottom. So it does overlap. This is where we would expect it to be sprung around the groove, but there's no groove yet. So let's say okay. So it's placed. It's good. There's no groove. Next. Do we have any more 25s? 25. That's 35. That's 30. That's 30. So we're going to use 2 of the next one. So next, same thing again. Unfortunately, it doesn't remember ring, retaining ring, metric. Type in 25. Oh, missed it. There we go. And we don't, oh no, it's 35. 30. Yoo-hoo. 30. There we go. 30. It's not. Why? You can see there's other ones, heavy duty and all that stuff. We've not been hearing anything. We haven't been told anything out of normal. So go for just the basic. I don't know why it's not picking. Let's try that again. Trying to get to 30. There we go. So the black phosphate again, 10 for $10. Let's have a look at its details. Gonna take a screenshot of this as well. I need to know how big the the groove is. So that's what I'm trying to get here. And that looks like it's okay on my desktop. You can't see that. Just download that as a step. Again, 30. I'm gonna rotate this one into shape a little bit as well, or into orientation. Make sure it's not grounded. Okay, and a nice green. J for joint, inside edge, and top of the. Make sure it's centered right. I'm just going to shift this a little bit. There it is. That looks good. 180. And that's good. Say okay. How do I reuse that? All you have to do is click it once and Control C and V. And I'm going to move it around so I can see where it should be. So, no movements, just a copy paste. That's what shows up in the history. So if you want, just pull it away and do another joint, J, to the back of the bearing here, because this is also 30. So, okay. Last, got 3 ring grooves in there. Or sorry, 3 rings. This one is 35. Retaining ring, metric, 35. 35. There we go. And we should see not many options in the standard. And again, because we're just using the basic external retaining ring, black phosphate again, click it once, product detail, and I'm keen to see these things again. That's got a lot of information, its hardness, thrust load capacity. It also says some things, for example, PR is based on using a shaft that's harder than the ring. This is very common. That's why it gives it minimum hardness. It's for groove 33, 1.6, right? So we can use that. Insert or download. There's our ring. Just rotate it into place. Let it snap to 90 or minus 90. Say, okay, not grounded. Joint. It's on the other side this time, so this side and in what's going on here, top of the chamfer. That looks right. Say okay. It's unfortunately the color of the gear. I'm going to change its color. Go purple. So we have two of the 25, what's that, 25? One is a 20. Oh, hold on. 120, 125, and 130. Two 25s, 130. Sorry, blathering now. There we go. They're all placed. Now we have to fix the sketch. Now, because of how we've set this up, which is fine, I'm actually going to create a new sketch here. These are the cuts. But we need the cuts to be well out here because I want to use them now for the ring grooves. So I'm going to actually pull that cuts sketch all the way out here, layout cuts. That allows me to work on this as it's done right now. So I'm actually going to break a lot of the column rolls here and work on a sketch way out at the back. There it is with our memory thing, but we'll just leave that. So next, what I want here is I need to project something. So I'm going to be interested in these shapes here. So top of the shaft, I'm going to actually pick those 4 lines. It's hard to see I've selected them, but down here it shows 4 lines, 4 sketch curves. And just press P, so I've pre-selected. Keep the link on, so then when you move these, it'll just adjust and show. Say okay. Can hide that first sketch if you wish now. You can also hide the body if you want. So we can see what's going on. Oh, you can see what's going on here. So we now have some stuff that we're interested in. So one thing I am also interested in is where to put the groove. It's tempting to match it up to the ring. But what I want to do is go with, I think, myself, is match it up to what's positioned in the ring itself, kind of like we would in reality. So I'm going to also project, no, I'm going to do a intersect. I'm going to intersect these edges, so that's ring positioners. So there's one here, essentially the same ones we used for the joints. Because the rings have a slot, we can get in there nicely and pick them. That's good. That also shows us where we're positioned. So there's 4 selected again. Say okay. We can now, if we want, hide all the components. And we can kind of see what's going on. Now, say we forget what's going on, we can always turn it back on. So the ring is on this side. So let's do a line. This is going to seem a little strange if you're coming from SolidWorks. I'm actually going to snap to that. Come all the way down, around, and back up. Gives us a groove, but it's actually showing what we're attached to. Hey, I'm attached to this dot here, this projected intersection. So this is our, what size is this? It's about 23 or so. This is the small one. Let's have a look at our screenshots. That's our first one. Oop. So we're looking here for a groove I'm using the Mac, so I can just highlight it. The diameter is 23.9. So, oh, we don't have a line here yet. So let's show this guy. We'll project that. Make it a center line. Dimension 2. It'll zoom out. Depends how your settings are going. Notice it's inboard of the ring. The ring has to be snapped onto this, so it should be smaller in this, in the way it is right now. Get it right here. So it should be smaller. And our width is 1.3. Again, making some assumptions here. But for now, see a little bit of a gap. It's this is, and I'll spend a little bit of time talking about this. The dilemma here is, how do we size it up against the bearing, or do we size it up against the ring, or do we center it? These are dilemmas that we have to deal with. So we've got this edge here that we've snapped onto. One option is to actually size this and snug it up against the ring, which would make sure the ring is pushed up against the bearing. This I would believe this breaks some Orlov rules, which is over positioning objects. We're then assuming that the shoulder, which is back behind the bearing, is perfect. I usually model this as shown. Depends where you are and what people you're working with, and how keen they are about tightness and all the rest. A lot of people center it, which is fine. If we look at the first bearing here, there's tons of room here, so we could move this further in without interacting with this bearing at all. I'm going to leave it where it is, but this is something that should be talked with. Talk to your colleagues or your machinist about this. Like, where do we put this ring? So for example, you can now dimension, like, where's the ring start? 6.7 is an inspection dimension. Like, you could shift this over to be, 6.8, whatever you wish. But for now, I'm leaving it as is for clarity of modeling. But just be aware, this is a dilemma that comes up frequently. We're done our first ring groove though. Let's go ahead and do the rest a little bit quicker. So next guy is our hub, and it's got, I believe, this ring right there. So let's do the same. I'm going to do this a little speedier. So make it a big so I can dimension it and get a hold of it easy. And we actually have two. Now where's the other one? It's on the far side of that last bearing, right? Yeah. So let's do another one over here. Now this way, make sure we got the directions correct. So let's see both of these guys. They should be sitting inside of the groove. There we go. And our groove details. The groove diameter, 28.6. So we can just do one and match the other one up. So dimension, kind of try and stay from left to right. And our width, 1.6 for this one. Probably should have done the equals. Oh, probably should have done the equals first here. Make sure it's the right size. Looks good. Excuse me. Equals. And then we'll do an equals on this edge, which is between the size of the shaft and the diameter, or the bottom of the groove. Again, you'll see it slightly off, but it's because the ring is back out of the center of the shaft here because of that slot. There we go. So again, discussion as before. Those are looking fine. Last is that in-betweeny gear, the big one, and its larger ring. So let's do that. Line. I'm making this big so I can easily dimension to it. Let's look at our screenshot of that. This should be our largest. Groove 33. Oh, that's not right. Groove 33 in diameter. No, losing control here. And again, 1.6 for this. Sometimes things get in the way. It's maybe time to hide some in here. And depends where you want it. It's up to you where you put the dimensions. Usually just move them out so you can see them easily. And put the diameters under the groove itself. This is just controlled by an equality. That's it for that. I'm going to show the body, hide all the components, and show both sketches. So this is our cut. We want to do a cut here. So let's go ahead here and pick that. So revolved cut. And you can actually just draw little boxes around these things. Quite easy. Nice. Should have 4. Axis is in the sketch. Now, which axis am I using? It doesn't really matter, but let's go ahead and hide the first one so we're picking the right axis. Objects to cut should just be that body one. There it is. Let's have a view of everything at once. V to turn it all on. Things are getting a little busy. For example, these joints, you can hide the joints in the sketch. Let's make sure everything's looking good. Layout cuts. Why is that not? Oh, right. There it is. So, grooves and rings are placed. Everyone's looking fine. Next, let's go ahead here and take a stab at the keys. Now, keys are driven by the shaft diameter at that point. There's going to be 2 keys in this part. We could use splines, we could do all sorts. Well, maybe not. It's a bit tight. So maybe key is the only way to go here. And obviously, we're also being given a key slot in the parts. Let's go ahead and adjust this analysis. One way is we can have a second analysis turned on. We can also just adjust the one we have. Let's just rotate it the right way. So there's our keyways in the gears. So this guy has to be centered, obviously. So in the layout cuts itself, let's go ahead here and place that. Now, you can see here we've got 2 parts. And one thing to notice, we're not snapping to this. This is the outside of the shaft. We're snapping to the middle. So I'm actually going to put that coincident with the origin. So let's edit the sketch. We don't need the bearings right now. Let's hide those so they're not in the way. Nor do we need any of the rings. So just the gears, just showing. Now we can also turn on slice, which will give us a view kind of perpendicular to the sketch. So we can, if we turn slice back off, we see both. It kind of turns off the analysis. Just have to be a little aware, so slice is fine. So I'm gonna place this guy against the origin, middle of the shaft. Make it 50 long. We're not doing calculations here, so we assume that that's fine. Next thing is I want to position this correctly in the middle. I'm going to position them in the middle of the gear. Maybe this is not what you want. Again, you would be talking to older gents or ladies around. But the key thing here is just to be methodical, move it later. I'm going to do this with just geometry, so P project. Oh no, I'm going to do an intersect again. We've got one here already. Let's do this top edge. Why am I doing this? Well, now I can actually just snap to these guys that we already have. I'm gonna just connect them up, make sure I get the right one. So the two top, there we go, escape. Double click to make that construction. And now all I need to do is put this to the midpoint of that and then make them equal. It's a little hard to see what's going on here. We could hide the bodies. That's what we've got. Still not defined because we don't know the size of it yet. Now, let's turn off our slice. Even inside of the sketch we can ask stuff. So how long is that? Oh, 8. And the shaft here is diameter 30, radius 15. Let's have a look at our specs. So let's go over to, if we can, our lecture. If you watched the previous video, you might have seen this stuff come up. For us, we're looking for DIN. This is metric. We're DIN 6885. Keep in mind that. And our shaft diameter, well, oh, here it is. So we're looking for shaft diameter from and to. Our shaft was what? Let's check. 30. Oh, I'm in the wrong thing here, sorry. 30. 22 to 30 or 30 to 38. It's usually up to and including. If you're worried about this, we always, well, at least I do, always reference back to ASME. This is old, 67. Let's look at their charts. Where did they go? It's up to, sorry, over and including normally. This is old school, but so it includes this, in this case, 7/16. Not, so if it's 7/16 exactly, we're using this first row. Do the same over here. So let's look at that, standard. So we're going up to and including, so that's an 8 by 7. Nope, yeah, 8 by 7. So the breadth on the rounds is 8 and the depth is 7. Let's have a look again. Are they following that? 8, so not 10. So they're doing the same as us. So that's it, up to and including. Perfect. So now, while we're here, if we can kind of reach through here, it's hard to see, but there it is. We're going to make that 8. Nope. Get out of there. 8. Does it go fully defined? Nope. What's going on? Oh, we added something there. I'm going to slice because it's getting in the way. Let's do that again. Dimension across the flats of what will eventually be the flat of the slot. 8. There we go. Now, we're going to cut that out, but let's do the other one while we're at it. So, same approach. I'm going to do an intersect. Can't see it's off screen, sorry. That top guy. Got one over here already. So let's draw our slot. So we're going to draw a overall slot. Can snap it onto this point here if we're being fast. Don't know the size yet. Its length is 50 again. Let's do that. These are 60 long, these hubs. Gives 5 at each side if we center it. And again, because we don't know more than that, let's do that. And 2 lines to the top. So again, making sure I got the right piece. There it is. There it is. Center or midpoint constraint on that guy, and then equals. See, snap into place. Everything looks good, except for the size. Let's turn off slice. Skipping ones in case I do something here. 10. Okay, 10 is what they're saying. 17.5, 35. Let's have a look. Up to, okay, so 30 to 38 is 10. There we go. Height 8. 10 by 8. Got an 8 by 7, 10 by 8. That's good. So slice again and dimension that 10. We're going to actually drop our model the slots in here first, and then hopefully go up to McMaster-Carr and have a look to see what they've got. So let's do it in that order, just to make a point here, because this is standards driven, so we should be good with that. I'm going to hide the two gears because I don't want to cut them, and let the fun begin. How far do we cut? How do we cut? So extrude, do them one after the other, more or less. Make sure we're going the right way. There's the cut. Oop, there's the cut. And the extent type might be, why don't we just go to all? Make sure we're only cutting that one body. That's the shaft. There we go. How do we, because that's not right. Like if we look at the standards here, it doesn't go all the way in. So 1 is high type, 2 is low type. Let's try high type, it's more standardized. You can see it's just right up here at the top. It's not right from the middle of the shaft, of course. So we have to figure that out. So, well, T4 is maybe useful, T4. So for our 8, what's D? Hold on here, we're getting all confused. D is 25 on the first one, 25. 25, where are you? There you go. And then B is 8, right. And H is 7, right, we got that. So H is 7, 25. So, well, hold on, this looks easy. T4 is just 4. So maybe we can use that. So 4 down from the top of the thing. So let's try that. So we can actually, oh, lost our cut, there we go. We can actually start not from the profile plane, but from an offset. Type in an offset just to try it. Oh, that's good. So what if we started at the diameter, or the radius, sorry, 12.5. That doesn't look so bad. But what is this diameter? Oh, we've got angles and everything. Cancel that. Sorry, let's get this right. So radius is 15, sorry. So we're at 15 and 17.5, right. So let's make sure we've got this right here. 30, 8 by 7, so it was 30, 4 down. We were looking at 25 before, that's not right. So 30, this is all very convoluted. So let's try that again. E, cut that guy out, do it all the way. Distance, all, profile plane, offset. Let's just try our radius. Like if we put in 15 here, it doesn't give us anything because we just went right to the side. But if we say 15 minus 4, that thing from the chart, that does work. So let's just make sure we're getting this right. So if we said 14.9, yeah, tiny. So that's good. So 15 and then minus 4. So let's check again. 15, we're on a 30 diameter shaft, 8 by 7, that's H, 30 and 4. That's the standard, that's what we're gonna do. So let's do the next one. E for extruded cut, cutting all the way to begin with, distance all. Let's go for offset. Now that was 35, so let's try 17. Should give us a tiny cut. There we go. 0.5 disappears, minus, well, what was it, 4? So 35, oh, it's 5, so let's do that, minus 5. Let's get some parts, keys, machine keys, rounded machine keys, metric. Now, what are we going for here? Width. Let's do the first one. That was, what was that? That was 30, 8 by 7. So the width is 8. Notice we don't get height. It's controlled by the standard. What if we can get 50? Oh, 50 is what I want. Jumps around a bit. No, we only have two choices. Stainless, undersized. Oh, there's DIN 6885 again. Is that what we had before? Yep. Perfect. So that is the right guy. $5 for, sorry, $5 for $10. That's good. We can have a look at this. Gives us a preview. No chamfers, it looks like. And it's undersized, meaning it'll fit into the same size slot. So tolerances, GD&T, all that stuff. We don't know what we're going to be doing here. Undersize meets the DIN standards and it makes things disassemblable. Let's just add that guy. That looks okay. Let's rotate it into place and rotate it into place. It's not in the right orientation. Just get that thing out the way. So I kind of want it in there. So say, okay, not grounded. I'm just going to joint that into place. It's easier than you would think. Just pick the middle. If you get the correct orientation, it makes it easy. Fits in there snug. We'll talk about that in a second. Say, okay, let's have a look at the first gear and turn on our, let's look at that. We should see a gap here because of machining tolerances. Like you're gonna have a small fillet on the inside of this, a notch. But let's see how far apart these guys are. 0.3, it's good. It's normal, it's what we want to see. However, it's too tight at the ends, right? The end of the slot is really touching the end of the key at both ends. Let's turn on our layout cuts dimensions. Again, it depends where you work or who you're talking to, but I'm going to add 0.5 millimeter here. So for a 50 long key, I'm going to actually make the slot 50.5. It depends where you work. Some places will go to 50.4. Some will go to 51. It depends. I'm just going to go to 50. Actually, let's go to 50.4. Sorry, after all that. 0.2 at each end. 0.2 of a millimeter. We're going to have the same problem on the other side, I suspect. Let's make that 50.4 as well. Won't adjust our joint and gives us the correct fit. So no fit at the end of the key. Again, if we move the sketch, the key will go with it. Let's try the next one. So leave it, I'll hide that one. And we'll come back and have a look. So this guy is 35. Key, round, metric, width, 35, 10 by 8, 10. Notice these are just standardized lengths. 50 is available. a little bigger. There it is, dsgn380, perfect. And it's just carbon steel, don't need stainless or anything like that. We can just download that guy immediately. Pull it in, kind of get it into place, so rotate a couple times. Just to make the jointing easier, I can do it from the top here. Grab that little pad, pull it into place there, so don't ground joint. Again, unconstrained first, fully constrained after. Say okay, check it against the gear. Big gear this time, turn on analysis. So we got there to there. 0.3 again. Looks like the standard is working out just fine. Now, some of you will be saying, well, this is not perfectly centered and all that sort of stuff. That's fine, right? The standard overrides, as far as I'm concerned, overrides things that we can argue about. But for now, I'm going to go with the standard as opposed to long discussions about whether the key should be perfectly centered in the shaft on the edge, half above, half below sort of thing, like our calculations assume. It is slightly off. We can do some graphical analysis of this if we wish, maybe for a future video, but for this video for now I'm leaving it as is. Both our gears are now keyed. Now, last and maybe least, no, not least, we're going to go ahead here and do some filleting and just get this sorted out. So everything's looking okay. The temptation here is to, and it's not a bad temptation, is to fillet everything, including those ring grooves and keyways and all that sort of stuff. That it does work, and the CAD can cope with it, and it's perfectly fine. But in my opinion, maybe I'm changing over the years. I used to do this and check for interference with the keys and the edges and all the rest. This is more discussion with your local machinist, who definitely is kind of the final say on this sort of stuff. But the goal here is to follow the standards and assume that ultra micro detailing, for example, the radius of the tip of the milling bit will be accommodated by that 0.3 gap. Same with the ring grooves. There is, for example, in the calculations, an assumption of the radius of the tool bit inside the ring groove. We're going to stay away from that in this video. Not because we're afraid of it, but just it's fairly normal to leave that unmodeled. So just to keep it work oriented, let's not model those tiny fillets after all that. Let's have a look at the analysis. I'm going to change it back to the other orientation, or halfway in between, whatever you wish. And I'm going to just focus on the fillets underneath the components, the main components themselves. Let's look at this bearing first. Actually, let's start at the other side. Let's look at this bearing. Right? Luckily for us, Fusion is smart enough to say the radius of that fillet is 1.1. Let's have a little gander at the standard from SKF themselves. Let's make sure I've got some stuff here. Let's have a look at the SKF bearing. This was the 6305, the first one. 2Z. Nope, not the right one. The 6305 PDF. There we go. It tells you, again, we haven't later, next couple of weeks, we're going to be dealing with specifying bearings, but this is the numbers we're going to be looking at, load ratings and all the rest. For us, not worried about that too much yet. We can see the shields, all that sort of stuff. And importantly, some sizing. For us, we're interested right now in the dimensions of the abutment, as they call it. I'm going to make this a little smaller so we can see it. Ooh. The problem that we're running into here is that we need to know what RA is. RA max 1. Where is RA? There it is. So RA is the radius that we're allowed for the fillet underneath the fillet of the bearing, if that makes sense. So RA is given to us as max 1. I tend to use a parameter for this. So let's say S, look for parameters. I'm gonna add one here, sharp fillet. And it's 1 for now. Let's see how it goes. And then as per SKF. Before we get carried away here, we have to check the other bearing. So this is our 6305. What about our 6206? There's RA again, where it's on the next page. There we go, RA max 1. So it's the same for both. That's good. Shows us how we might want to attach our bearing into a housing. We'll come back to this in the next couple of weeks. For now, all we need to know is RA for now. Perfect. So we're going to stick with the 1. Let's go ahead and do that actually. So F for fillet. I'm going to pick, again, just in case I pick the wrong thing, let's hide everything the long way. So RA, our sharp fillet. And we can start typing sharp. There it is. Say okay. Turn the bearings back on. Wait for it to adjust. There we go. There's a gap, which is what we want. So the fillet on the shaft runs out before the fillet on the bearing, so we don't have interaction there or intersections trying it on. Oh, this is really tight. Now 1 millimeter is not such a bad, that's quite a big sharp fillet, and maybe even unexpectedly large. See here, we've got a bit of a problem with the way this is modeled from SKF themselves, so I'm a little concerned here. Oh, phone's going crazy. So what we're after here is, sorry, turn off my volume. What we're after here is fixing up this thing. So let's go with S parameter and change it to 0.5 or 0.6 or whatever, but let's go for 0.5 for now. And we can see we now have an easy gap here on both sides. So this is fine. 0.5 is not a bad sharp fillet. Let's turn on the 2 gears and have a look at them. These are actually quite small. Right, so I'm gonna ask, what if, oh, highlighting like crazy here, sorry, flickering. We don't get a thing here, so why don't we try using the measure tool? How about from there to there? 0.75. It's quite small, right? 3/4 of a millimeter on a chamfer is small for a gear. And we're kind of getting pushed into, maybe we should just use that same sharp fillet for everything. Let's do that. So let's edit our fillet. Keep that row. If you want, this is maybe not a bad thing actually. Let's do that. Let's add a row. Pick 2 more edges. See if we can get in here carefully. There it is. And the other one underneath. And call that one sharp as well. Yeah, it's the same, but it'll be clear to somebody looking in the future that we've got both using the same sharp fillet. There we go. Everything is kind of done. One last thing. Got a bit of a overly long stub sticking out here. So our measurement here is 4.7. We don't need 4.7, like, you know, arguably. And we could shorten it up. We also have quite a big chamfer here, that's okay. But 4.7 is a bit much. You could argue it should be as low as 2. We could take, or even less, like 1 or 2. let's take 2 away here from this length. What about this side? 5.4. So we could take 2 away from each end. That would keep things symmetrical. So let's do that. That'll decrease our shaft slightly. How do we do that? Well, this is really tension causing here. What if we planned this whole thing out badly? Right, so will it all move correctly? Let's try it out. So the moment of truth. Did our plan work? 25. I'm going to change that to 25 minus 2. So I'm going to leave the 25 behind. Let's see if it works. Oh, right. So 200 is stuck. So let's undo that. And we'll actually go in and edit the sketch. The 200 I want to change. I'm going to change that to driven toggle. You didn't see that. And then this one, I'm going to toggle to driving. So I want to keep the 10 and leave the 200 to shift. It runs back to where we were. Now let's try 25 minus 2 so we can see it. Oh, perfect. We're down to 198. Same over here. 25 minus 2. We're down to 196 on the shaft length. Not a big deal, but it's easy to move the end stubs with this whole method, so it does look like it works. We can adjust all sorts of things in here. So for example, this last move we just made didn't adjust the positioning of the 2 gears. So for example, we don't want to change 10. That was the whole problem. So if we were in a housing and we're expecting 10 in between these 2 gears, we can't just change that willy-nilly. However, we can change the end of the stubs to at our convenience. So for example, well, maybe this is a little bit too long. Maybe we want to go to 22. We can do all that stuff as we wish. But for now, let's leave it at 23, 70, 10, 70, and 23. For those who are following along for marks, let's leave it at that and figure out what our volume is. So, bodies, we'll turn off our analysis here. Turn off our sketches so we can see what's going on. I'm only interested in the volume of the shaft. So we can hide everything else, including the body. Where is our part? What's going on here? Oh, sorry. I just accidentally made the key active. Go back to the top. This radio button up here. There it is. So that's our shaft. That is done. Not very interesting in the end without all that stuff on it, but it's, yeah, there it is. Let's get the volume for that guy. Body 1, if we want to rename it, now's the time. And our body is properties. That's a lot of volume. Let's cancel that. I'm actually going to make this into a component. So componentify it, create components from bodies. That's not a good color. That'll do, well, greeny blue sounds good. Let's have a look. Everything's still good. Just hide all that again, undo. And I want to know the size of the shaft. I'm going to change document settings from millimeters to centimeters. That'll give it to me in cubic centimeters, better known as milliliters. Volume 153.8767. Give you a little bit of a range, but that's what we're after. Volume of the shaft. If you followed along perfectly, you should see the same number. We haven't dealt with material and all that sort of stuff right now. It's just steel. This is our chance to pick different materials for everything, all that sort of stuff. But for now, just go for volume 153.8767. That's it for me, finally. Thanks for watching, and over to you.